Come on. Yes, now it is. Okay. Oh, is Tipper not coming? Or
She said she just left somewhere. She's gonna try to make it.
okay. Okay. Thanks. Everyone else is well, actually not. Yeah. Pretty much everyone else is accounted for one way or another. Okay. So, method I started to talk about. Last time, Newton's method. So this is section 10.4. So we'll do a first half of the section today, and then the other half will be after spring break. Check if you look in the site. I've updated the schedule. So the midterm will be April 3rd. So a bit more than halfway through. To avoid conflicting with the modern algebra test that Dr. Cole herself told me would be on March 27th.
Our retake is going to be April 2nd.
Yeah. Okay. So I've adjusted the schedule accordingly. So, and then there will be a homework due the week after spring break, like on the 20th or 22nd or something. So the homework 5 has been put up. It's on stuff I've already covered, so you can get started on it at any time. So good luck with that. And I may have another quiz to put up. If so, I'll get to that soon. Okay. Now, so as far as we're going to see Newton's method. I derived it one way last time from fixed point iteration, but now I'm going to derive it a different way that I think will be a lot more intuitive. And then there are certain favorite examples that I like to do. One is using Newton's method to compute the square root of 2, or the square root of any number, using only basic arithmetic operations, so addition and division. And also, another favorite example is how to accomplish division, in other words, the reciprocal of a number, without actually performing any divisions. So using only the other operations. And then some convergence analysis. Because we've seen two methods, bisection and fixed point iteration, that converge linearly. And also what the asymptotic error constant is. So what will it be for Newton's method? And then actually, I'll probably run out of time by that point, but we'll just see what happens. Okay. Oh, actually, what? Okay, yeah. Okay. And then double roots. I talked about multiple roots. Double root is when the function is 0 at a point and the derivative is also 0 at that point, and how that can cause a problem for Newton's method. Okay. Yeah, this is my last activity before spring break, because I will not be here tomorrow. I'll be driving away from this place as fast as I can.
Oh, you don't hate us that much, I hope.
He has to do my reference letter first.
I don't hate the students that much. All right. Anyway, before I incriminate myself. Okay. So, the derivation of Newton's method, it boils down to this question, or these two questions. So for what kind of function f is this root finding problem that we have, f of x equals 0, easily solved. So what is the simplest case? And then the second question will be, how can we use this, the result of the first question, for general cases? Now these are the same questions that were posed at the very beginning of the semester for ax equals b. For what matrices was ax equals b easy to solve? Diagonal matrices, triangular matrices. How do we reduce the general case to that? Gaussian elimination. So pretty much any kind of problem we're trying to solve numerically, this is how we approach it. We look at these easy cases and then see what we can do with that. So for the first question, what kind of function of all different kinds that are out there is it really, really easy to find out where it has a root or where it's equal to 0?
You have an intermediate value there? What'd you ask?
For what kind of function? I mean, there's functions like trig functions, exponential functions.
Quadratic.
Okay. Quadratic is easy because you can always use a quadratic formula.
That's right.
What's even easier than that?
Linear.
Linear. Yes. Because if it's not a vertical or horizontal line, so I mean vertical line versus actually a horizontal line, there's either no root or infinitely many roots. So any other situation, there's going to be a root. So y equals mx plus b. So we can just find the solution. X star is equal to minus b over m. Okay, so now how are we going to take advantage of this when we have a function that is nonlinear? We'd like to incorporate this somehow. So for that, look at how can we approximate any given function f of x. Now we're assuming that f is nonlinear. By a linear function. What would be a sensible line that we could use? Yes. Yes, that's exactly it. Now, that will only help near a particular point, where it's tangent. But that's all we got. That's what we use. Yes, the answer is a tangent line. Okay. So you started your lucky guess or something?
I thought about that.
Okay. All right. Okay, educated guess. Okay.
I'm just real worried about yesterday, so I bet anything that comes out of my mouth is going to be yes.
Okay. Wow. Well, I guess my midterm's not going to be nearly as interesting.
Well, I certainly hope not.
Also, so you're not happy with real analysis either.
Well, I enjoy interesting problems. One just doesn't want to see them on an exam.
Good point.
I think this is the first time I agree with that.
Okay. All right. So here's what we can do is I'll make a graph here. Okay. All right. So here's our root x star, but we don't know that yet. That's what we're looking for. So I'm going to pick a point out here somewhere. x naught. So this is just like a fixed point iteration. This is our initial guess. So what I can do is come up with the tangent line to the graph of f. I'll try to draw this correctly. That's a pretty lousy tangent line. Actually, what I should do is make the graph a bit more curvy around here. Because the graph itself was kind of like a line, and that kind of spoils my illustration. Okay, that's better. Okay, so here's x star. And I'll keep x naught over here. Okay, so now my tangent line, which is kind of a struggle to draw, is here. Okay. All right. So we need the equation of a tangent line at this point, x naught. Now, in my other class, I teach Math 102 online. And they're frequently given a problem for different kinds of functions to find the equation of a tangent line to a given function at a given point. And they don't get it right very often. So I'm hoping that you all, being either math majors or math graduate students, particularly the latter, can do better. And so what is the formula that I would put here for, like if I want to express it in point slope form, which would be easier, for the tangent line of my function f of x at this point, x naught?
Are you asking for point slope formula?
Yes.
Y minus y1 equals m times x minus x1?
Right, so what would be the y1, the m, and the x1?
You're using your x naught
Mhm.
for your x1. Y and x stay the same, and your y1 is the point up at the top. That it is.
Right, which I would write as
Fx naught. Yeah,
Yes.
same.
fx naught, okay, plus, yeah, so like you're saying
So
y
something-
minus y1 equals, and my slope?
What's the chain? We don't know. It's the. Well, he's whispering in my ear.
Okay. What's the slope?
Your turn.
Yeah, like that.
Is f of x naught minus f of x1 over x naught minus x1.
Oh, that's a secant line. I want a tangent line slope. The slope of a tangent is given by the
The derivative.
Yeah.
Okay.
f prime at x naught. Yep. That secant slope will be important to us next class, though. And then times x minus x naught. Okay, so that is our tangent line. But now we need to set this equal to 0. So if I take this equation, and now, well, really this equation, set equal to 0, and I solve for x, what would that be?
Negative f of x naught divided by. I can't see it now.
Anybody in this side of the room want to complete it?
We're
F
gonna
prime x
distribute
naught.
from
Yep.
f prime x naught, and then plus the x naught.
Yeah.
F
Okay, yeah, there you have it. Okay, and that x-intercept is right here. So I'm going to label this as x1. So that's my next approximation, which is certainly better than where we started. So that's how we get the x-intercept of a tangent line. So now, what we can do is, okay, that linear approximation took it as far as it could. Now we forget about it and use a tangent approximation here at x1. So if I draw this tangent line, to get a new value x2, that's undeniably getting, dang it.
Outcome.
Okay. Undeniably getting us closer to the root, and that would work the same way. x2 is equal to x1 minus f of x1 over f prime of x1. Okay. And if I were to continue this process, then we would just keep going, and see now we're getting really close. You can barely distinguish x3 from the actual root on the board. So that's the idea behind Newton's method right there. We approximate f locally, around our point, by a tangent line, see where the tangent line is equal to 0, and then from a new approximation, update our tangent line and repeat the process. So we just keep finding x-intercepts of tangent lines in the hope that those approximations, those x-intercepts, will keep getting us closer to the actual x-intercept of f. Okay. So the result of this is, well, I'll just use a fresh board. It's just an eraser in this room. Like, what happened if we were talking to your class? Oh, where's the other eraser? But that's it's like it's all white. And look at this. How's this good for erasing anything? Yeah, especially on, like on the screen here. Like, okay, okay, that's a little better, but sheesh. Okay. Okay, so all right, so Newton's method is, so the algorithm, we choose initial guess, x naught, and then we have a loop that will keep going until we achieve convergence. For instance, if the successive iterates are close enough to one another, and it's just this step, xk plus 1 is equal to xk minus f of xk over f prime at xk. All right, and that's it. I mean, so yeah, there will be some extra code in here if you're doing this in MATLAB to carry out a check for convergence, but otherwise, this is it. Now, I should mention one drawback. There will be other drawbacks, but unlike the previous methods that I discussed, bisection and fixed point, the derivative is required. And that might not be feasible. What if because the derivative is another function you have to evaluate, maybe more expensive than the original function to evaluate. So next class, I will give an easiest workaround to that, where we use, instead of a true derivative, we use an approximate derivative, the slope of a secant line instead of a tangent line, and that leads to what's called the secant method. So that will help with that situation. But so just wanted to quickly point that out. Okay, so now that we have the actual method, I want to illustrate its use. Some interesting examples. So suppose your function is, say, x squared minus 2. Now, now we know what the root is. Pretty easy to get. So it's plus or minus the square root of 2. But we want a numerical value for it because it's not a perfect square. So how can we get that quickly? Using only the basic operations. Addition, subtraction, multiplication, and division. So So f prime of x is equal to 2x. So then our Newton iteration is the following, that xk plus 1 is equal to xk minus, so up top I'll have the function, so that's xk squared minus 2 all over the derivative, 2xk. But now what I'd like to do is simplify that. Now, I won't go through, whoops, sorry about that for people who are watching. I won't go through the algebra here because you all know your algebra, right? I don't even mean modern algebra. We're talking easy algebra. Stuff some of you help students with in the math zone. It condenses to a pretty simple expression, xk over 2 plus 1 over xk. So just by carrying out this process using just two divisions and an addition, it turns out you can get to the square root of 2 pretty quickly. So I'm going to show you some iterations now. And I'm just going to use an initial guess of 1. So if I go ahead and plug that in, x not equal to 1 to get x1. So that would be 1 over 2 plus 1 over 1, so that's going to be 1.5. And then I'll plug that in, because square root of 2 is like 1.414, 2135, etc. So getting warmer. So then we have, okay, so now we have 3/4 plus 1 over 1.5. So it's going to be 3/4 plus 2/3. So that's going to be 17/12. So that's going to be 1.416 repeating. So we've already got the first two decimal places correct, and we're looking for 1.414. So that's encouraging. And after this point, I would not want to try to do this in my head. Okay, so if I do, all right, so x over 2 plus 1 over x. Okay, so now I'm going to write this out to as many decimal places as MATLAB will display. So 1.414, 2156, 86, 2745, 10. That's a lot of decimal places. Now if I do that again, okay. 414, 2135, 623, 74690. Okay, and then again. All right, x5. 6237 3095. And now, if I were to do this one more time, x to get x6, it turns out no change. All these decimal places would be exactly the same. So at this point, we just say that this method is converged. Because we get that many decimal places of accuracy, I think it's safe to say that we can stop. Now, okay, good to know. Now, what I want to indicate on the board, now that we have these iterators in front of us, is every time we took an iteration, how many decimal places did we have correct? Because with linearly convergent methods, we had the rate of convergence. That's like minus log space 10 of C. That indicates how many decimal places you get correctly per iteration. So for instance, if you have a linearly convergent method and C is equal to 0.110, then you'll get 1 decimal place each time. But what about this method? So I'm going to put a box around the correct decimal places. So, well, first couple of iterations, we only had 1 decimal place correct. Or here we have two digits correct past the decimal point. Next we have 1.414121, so that part was nailed down. And then we have
3, 5, 6, 2, 3,
7.
Yeah.
Yep. And then everything. Okay, so notice the number of decimal places increased pretty dramatically from one iteration to the next until you pretty much had everything except for round-off error, and you can't really expect any further accuracy past that point. So what we often see in examples of Newton's method is that the number of correct decimal places roughly doubles from one iteration to the next. And you can see it even more easily from looking at the error in these iterations. In fact, if I were to go back and recompute these here, but then show the error, okay. All right, so if I write the error in scientific notation, starting with, okay, yeah, I'll do it over here. All right, okay. So for like 1.416 repeating, the error is roughly 2 times 10 to the minus 3. And then, oh, right, okay, I have to do this on my computer. Okay, so, all right, the next one is roughly 2 times 10 to the minus 6. And then if I do it again, so roughly 2 times 10 to the minus 12. So notice the exponent is doubling from one iteration to next, 3, 6, 12. And, but then that trend won't continue, and it still decreases quite a bit. But because of the limitations of computer arithmetic, round-off error, that's about all we can hope for. But the point is, it's not like bisection where we would have needed like maybe 50-something iterations to converge to this level of accuracy. Here we can get the same in only 5. So that's a much more rapid form of convergence. Now, I won't say yet exactly what kind. We will discover that theoretically a little later on. But I wanted to illustrate through an example, here's how rapidly it converges. Okay. And which is one reason why Newton's method is one of the most popular root finding methods out there, because of how effective it can be. But as this next example will show, it's not always. Okay. So what about this function? F of x is equal to some constant a, so some positive constant you've chosen, minus 1 over x. Now, if we set this equal to 0, what is the root? One, you out. Sorry, what?
He was saying x does not equal 0.
Well, yeah, we can't. You have x equal 0, but no, but we said f of x equals 0. Then what would x be? Yeah, so
Simply the inverse of a.
yeah, so 1 over a. So in other words, f of 1 over a is equal to 0. Okay.
Yeah.
All right. So the solution to this equation is a reciprocal of a. Now, like, why are we doing this? Well, something interesting happens when we actually describe what Newton's method would do in solving this equation. So, what's the derivative? Well, what?
That's
One
f of x.
No, yes, yeah. What's the derivative of this?
Okay, it's negative x over, what's x over x squared?
Yeah, 1 over x squared. Okay. All right, so now we'll use this for Newton's method. So xk plus 1 is equal to xk minus the function evaluated at xk over the derivative. Okay. But dividing by 1 over xk squared is the same as multiplying by xk squared. So I can simplify this. Okay. So once I simplify all this, and I won't go through all that because again, that's beyond you. That's not so advanced. I'll get another term involving xk here, which I'll combine with the first one. And I'll get 2xk minus a xk squared. Okay, so this is my Newton's iteration. Okay. Now, notice no divisions. So even though the result of this iteration will be the reciprocal of a, I'm not actually performing any divisions and getting it. So I'm actually dividing without dividing. Now, back in the 60s, IBM made a series of computers that actually used this approach to perform division in hardware. They did not have a division circuit like modern computers do, because computers normally have separate circuits for addition, subtraction, multiplication, division. So these kind of computers had addition, subtraction, multiplication, and then did division this way, because division is the most expensive operation for a computer to perform. And I guess back then they hadn't really figured out how to do that all efficiently, so they did this. And maybe, I guess, they improved division technology later. So that's why computers these days don't use this approach anymore. But it's an interesting case to look at. So I'm going to do an example. I'll let a be equal to 12, because that's my favorite number. Don't ask why. The root would be 112, which would be 0.083 repeating. So if I go ahead and make an initial guess, I'll set x equal to 0.1. Okay. So x naught is not far away, 0.1. So then I go ahead and carry out this iteration. I substitute this into here, and I get the first decimal place that's correct, a 0.08. And I'll just carry out a few iterations here. Okay, so then we want to see 0.083 repeating. So we start to get that pattern, 0832. And then again, okay. So our third iteration, oh wait, 3333312, and I'll just do one more. Okay, so now the threes get a little harder to count on my screen. was only 4 in this iteration, but in the next one, there are 9. 2, 7, 8, 7. Okay. And then if I were to do one more, I would have nothing but 3s after the 8. So essentially it would be converged to full precision. So again, it only took 5 iterations, like from the previous example, to get as many decimal places as we could hope for. So that worked out really well. Now, what if instead I make my initial guess x naught equal to 1? Seems like a nice generic initial guess to start with. Worked well for us last time. Oh, by the way, with the square root case, I chose 1 and got the positive square root. If I had chosen a negative initial guess, I don't get the negative square root. So now I'll try initial guess of 1. And then I go ahead and plug that in into here, and then I'm going to get 2 times 1 minus a is equal to 12. Well, that's going to give me minus 10. Not very encouraging. So if I do that again, then I get something even worse. I get minus 1220, so we're very far away, and just one more.
17863240.
Yeah, thank you. Okay, so minus 17 million plus. So it seems like we're not going to converge to 112 in this case. So naturally we want to find out, how could this have gone so badly? So it turns out we can get the answer by looking at a graph of this function, a minus 1 over x. Because this function has a vertical asymptote at x equals 0. Oh, that reminds me. One of my research advisors as an undergrad at Purdue told me about how at some university, I think it was in Texas somewhere, they had a new supercomputer. This is a long time ago. And they claimed it could solve any polynomial equation. And so they had a big ceremony, ribbon cutting, university president there, and they invite him to go type in a specified polynomial equation to solve, to show off its capability. Well, he's not really a mathematician. He just makes up something really simple, like x squared equals 0. And it crashed. Because it didn't take into account certain simple cases. So it's a bit embarrassing. Yeah. So you always have to be careful about that when you're developing mathematical software. Test. That's why I urge you guys to do it in your homework, because then I tested myself and lost points. Okay. Now, so the graph. So it's minus 1 over x, but shifted up by a units. So it will look something like this. And then there's also a horizontal asymptote at y equal to a. And then you have the other part of the graph over here. Okay. Now, so right here is x star, the root. So if I choose an initial guess that's pretty close by, like over here, then I get something around here, which, like this would be my x1. I pick a tangent line down here, and everything works just fine. But suppose I choose my initial guess. So this is a good initial guess. But let's suppose my initial guess is way over here. So I draw my tangent line, and look where the tangent line takes me. Way out here. Off the board. So I'm now on the wrong side of the graph, because now I'm going to go up here to draw my next tangent line, which will take me even further away. And this cycle will continue, and your iteration will diverge. So given the initial guess x naught, we have to require x1 to be positive at least, so that we remain on the right side of the graph. So let's take a look at that. Well, x1 is equal to 2x naught minus a x naught squared, and that has to be positive. So now if I take this equation, and I'm assuming that x naught itself is positive, I get this condition. X naught must be less than 2 over a. Well, it has to be greater than 0 also, but we're assuming that. So only if this, so if you take this inequality and rearrange it and solve for x naught, assuming x naught is positive, this is what you get. So we're very limited in how we can choose our initial guess. We have to be pretty close to the root as it is. Now, when I first realized this, the first time I taught this subject, I thought, well, that's like really impractical. Like you have to know something about your solution to get your solution. So why are we doing this? What's the point? But then later, I heard a now retired computer science faculty member here at USM talk about, over lunch at McDonald's, that he thought that Newton's method was actually the best way to do division. And I'm thinking, what are you talking about? You need a good initial guess, and you need this information about your answer to get the initial guess, and what the hell? So I thought about it later, and I realized, oh, he actually has a point, because of floating point arithmetic, computer arithmetic, and how floating point numbers are represented, which is something I covered last semester. But so in computer arithmetic, you do know something about a. You know its magnitude in base 2, because it's stored in the number. And if you know something about a in terms of its magnitude, you automatically know the magnitude of 1 over a. You may not know the significant digits, like in the mantissa, but so if you have some information about your solution that you can easily get, and that you can use to come up with an initial guess. So I actually have as one of the exercises at the end of a chapter, chapter 10, a problem all about this, where you can actually show how you can use a knowledge of floating point arithmetic to come up with an effective initial guess, and therefore a practical algorithm for computing reciprocals in this manner. So it's not as crazy as it seems. I mean, even though computers no longer do it because they found more efficient ways to do division, but back then it was a pretty resourceful thing of them to do, to use Newton's method when no efficient division hardware was yet available. Okay. So any questions about why this example played out the way it did? All right. So who knows, maybe give that exercise as a bonus problem or something. So. We'll see if anybody needs it after the midterm. So. I mean, I don't want mine to be as disastrous as Dr. Diggins by any means. It just might turn out that way anyway, regardless of what I do. Okay.
Yours isn't proof-based.
Well, not entirely, but.
Makes a difference.
Well, okay. All right. So now that we've seen, yes, Newton's method can fail, but we've also seen how when it succeeds really well. especially compared to other methods. I'd like to just describe that theoretically. So I'll show you a proper error analysis, just like was done previously for fixed point iteration. Okay, and let's see how well we're navigating through a section. So 383 to, okay. Okay, now, all right, and we're going to assume that f prime at the root is non-zero. We're going to need that assumption. Okay, now, so I'm going to write the error as a difference between xk plus 1 and x star. So that's the error after k plus 1 iterations. And I want to relate this to the error after k iterations. So we can determine, is the convergence linear, superlinear, quadratic, or whatever. So now the formula for Newton's method I'll put in now. So xk minus fxk over f prime xk. And I'm going to subtract x star from that side as well. And so basically I'm just taking Newton's method, subtracting x star from both sides. Now, what I'll do is Taylor expansion of this part right here, f of xk, around, actually, no, I don't want to do that. F of x star using my center xk. All right. So what would that Taylor expansion look like? I'd have f of x star, which happens to be 0, but that's equal to f of xk plus f prime at xk times x star minus xk. And then I'll take it to one term more. 1/2 f double prime at squiggly times x star minus xk squared. Okay, so that's some unknown point that's between x, so x star and xk. Okay, that's actually an e, believe it or not. Okay, so I'm going to use this Taylor expansion to replace f of xk. So if I just rearrange this, f of xk is equal to this, which is 0, and then minus f prime times all this other stuff, minus the second derivative term. Okay. So now what I'll do is I will take this whole thing and replace the f of xk up there with it. So what that will give me is my error after k plus 1 iterations is equal to my error after k iterations minus, but everything in here is a minus also. So this minus cancels with these other minuses to give me a plus, and that'll give me f prime times, again it's the error after k iterations, but except it's negative. And then second derivative f prime. Okay. Now, if I break this up into two fractions, let's put that same denominator down there and move my plus down. Okay. Then what happens is, in the first fraction, the f primes cancel. Look what I have now. Xk minus x star plus x star minus xk. All of it cancels. So, gone, 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 gone. So, almost everything is gone. And what is left? I have f double prime at an unknown point over 2f prime xk times the previous error, and it's squared so I can write it in whatever order I want. Alright, so new error is proportional to old error squared. What kind of convergence is that? Quadratic convergence. So that is why, that explains the very rapid convergence behavior that we see compared to other methods, the ones we've seen so far, bisection or fixed point. This is actually the fastest method covered in this chapter. Even more rapidly convergent methods are possible, they have their drawbacks. So this is a good balance between rapid convergence and efficiency and other considerations. Okay. Now, as xk converges, this quantity here that's multiplying the error squared is converging to f double prime at the root divided by 2f prime at the root. That gives us the asymptotic error constant. So I'll go ahead and fill that in now. Okay. Okay. So, if f prime at the root is non-zero, the Newton's method converges quadratically. With the asymptotic error constant, which I've labeled C in the past, is f double prime at the root over 2 f prime at the root, or in absolute value. This is why I had to require that f prime of x star is non-zero, just so this would be valid. We have no reason to believe that this quantity will be less than 1 for a given f, but it doesn't matter. Having a c less than 1 is only important for linearly convergent methods, not quadratic. So that's the scoop on the convergence behavior of Newton's method, at least in the case where the root involved is not a double root. Now, okay, still have some time left, not a whole lot. So the last thing I'll do today is so the last thing I'll do is give you an idea with an example of a case where the root is a double root. Let's see what happens. So f of x is x minus 1 quantity squared times e to the x. So because of the squared, x star is 1, but that is a double root. So the derivative, we need the product rule for that. And considering that other aspects of algebra and calculus have been a torture for you guys, I'm just going to go ahead and do this. So we have 2x minus 1 dx. Okay, so that's the derivative. And notice x equals 1 makes the derivative 0 also. That's what it means to be a double root. The function and derivative are 0 at that point. So now, if I look at my Newton iteration for this particular example, so I have xk minus 1 squared e to the xk all over this other stuff, xk minus 1 squared e to the xk plus 2 xk minus 1 e to the xk. Kind of a mess, but we can simplify this a lot very quickly. Because notice, every term here, top and bottom, has an exponential. Gone, gone, gone. Every term, above and below, has at least one factor of xk minus 1. So we'll cancel one of them. Okay. So now that we've canceled so many things, let's clean this up. So then we have, up top, all we have is xk minus 1. And down below we have xk minus 1 plus 2. So really it's, and actually what I'm going to do next is I'm going to put everything over a common denominator. So this denominator simplifies to xk plus 1. So when I put everything over a common denominator, what I get is xk plus 1 minus xk minus 1 all over xk plus 1. And once I simplify this as much as I can, sorry to the viewing audience again, there's going to be some cancellation. So this will cancel and that will cancel. So what's left is xk minus xk squared minus 1 over xk plus 1. I'm not sure if this is working out like I thought.
Is that supposed to cancel? The ones, are they supposed to cancel? Since that's being distributed?
Oh, of this?
Yeah.
No, because that is being multiplied by
that's what I was-
next
okay.
But I see the problem. Well, no, wait. Minus. Okay. Oh, that should be a plus.
Yeah,
Okay.
change it on the block.
Oh, okay. Something seems wrong though. Well, actually, no, it's fine. Okay, so that's the simplest expression I can get. But now what I want to do is I need to look at the error. So this is my simplest, because as we can see, the root is 1. So if I plug in 1 here for xk, I'm going to get 1, which is what you would expect. Okay, but yeah, really the error I need to look at. Like I did before, previous convergence analysis, only this is with a specific function. So I'm going to subtract the root 1 from both sides. So I take my final expression here, that's as simple as possible. And subtract 1 from it. And now I need to put that over a common denominator as well. So what that will give me is xk squared plus 1 minus xk minus 1 all over xk plus 1. And then these cancel. And I can factor an xk out of the numerator. So I have this times xk minus 1. That's the form I wanted. So this is the new error. This is the old error. So what kind of convergence do we now have? If we compare it to the result from before, how the new error related to the old error, what kind of convergence is it now? It's linear because the old error is raised to the first power, not the second power like it was over there. So this is linear. And to get the value of a c, we can plug the root into this part right here, and we get c is equal to 1/2. And in fact, I have a homework problem. I don't remember if I assigned it, but or I might, where you can actually show that in general this is true. But when a function has a double root, but not a triple root, but just a double root, it's always linear convergence, and the c is equal to 1/2. Now, can anyone tell me what other method that we've seen has the exact same convergence behavior? Linear convergence, constant of 1/2. Some of you have put that in on the quiz already. Or actually a few of you. Not many have done the quiz. So what method converges linearly, and its non-error constant is 1/2. So the error is cut in half every iteration. Bisection, yeah. Now, can I use bisection for this? For that function? What?
I'm saying no.
Yeah, you can't. Why?
Because of the double root.
No, double root's not a problem. What do you need for bisection to work? Okay, yeah, and what else? Bisection is guaranteed to work if you have what?
A point positive and negative,
Yeah.
and here we don't.
Yeah, this function is always positive. E to the x is always positive, and this is squared. So bisection cannot be used for this function. Okay. But Newton's method can be used, but doesn't work so well. It's possible to get around this. If you apply Newton's method to f over f prime, that function has a single root, a simple root, and then you would get your quadratic convergence back, but that's a very complicated expression. So I might have it in one of the exercises, I don't remember, but so it's an idea. But so that's one reason why having a single or simple root is important. The other thing I want to mention, okay, we have quadratic convergence under these conditions if the initial guess x naught is close enough. So we just saw an example, one with a division, where we should have got quadratic convergence, but if we chose a bad initial guess, it was too far away, then the iteration did not converge at all. So that's important. Now, it's not always essential. Like the example with the square root of 2, we could have chosen any initial guess whatsoever, and it would have converged to either a positive or negative square root. So, in general, and I'll show more. I'm about to run out of time, but and I just want to get out of here. But in the cases where the function does not change concavity, like so it's always concave up or concave down, you can show in certain cases like that even if you choose a far away initial guess, it's still going to converge and converge quadratically. But those are pretty simple functions that have that behavior. So if you have something rougher than, then you need a good initial guess. But a lot of applications where Newton's method is used, like differential equations, you do have a good initial guess. And we'll see this toward the end of the semester when we solve differential equations using these kind of root finding methods. Okay, so this is probably the most popular, one of them, methods for root finding because of its very rapid convergence, but it's not all roses. The iteration can fail, or maybe it won't converge as rapidly, or might fail to converge at all. But when it does work, we love it. So, but I'll talk about an alternative next class, the Secant method, and then we'll actually be done with this chapter. And then I can give you a test.
Did you move it already?
Yeah, I did, April 3rd. Okay, so enjoy spring break. I certainly will.